Thank you and good afternoon. It's a pleasure to be here and talk about organic semiconductors. Compared to the previous two speakers, we move about 20 years to the future now, and we'll see whether we'll reproduce such advances as the previous speakers have reported. The many advantages of organic PV are that it's a very thin film technology. It's basically a plastic film. It's flexible naturally, can be produced in roll-to-roll technology. It can be changed in color, not always brown or black modules, but you can do it also blue, green, or even red if you wish. You can make it easily transparent, homogeneously transparent, and you can easily adjust the transparency level. And this is, as said, homogeneous and not a silicon module with holes in it. So it's a completely new technology which has many new applications, and just to show you one example, you can make, for instance, roofs which are transparent, flexible, and there are many, many new ways where you can use photovoltaics at places where it was previously not possible. Now, the outline of my talk is as follows. I'll first want to give you a little bit an introduction to the basic properties. Can I ask the Chairman to start the watch, you know, that I see my time? Or otherwise I speak forever if you don't start it. And after talking about the basic properties, I'll discuss the main challenges which are going to higher efficiency, as always in PV. And finally, a few words about lifetime manufacturing and applications. Now, organic semiconductors are much less well known than maybe silicon, gallium arsenide, and CATL. They are usually deposited on large area, so it can be also on flexible substrates because they are deposited at low temperatures. They are composed of molecules. There are actually, millions of different molecules already around, and the variety is very large. It's mainly carbon, so it's a material which is abundant. And it can be very cheap because the amount of material per square meter of solar module is on the order of 1 gram. Organic light-emitting diodes are commercial. If you buy a Samsung phone, you use an organic LED display. But photovoltaic cells and organic electronics are still in a research phase. Now, I should mention that there are two different technologies in the field. The one is longer chain molecules, polymers, and the other is so-called small molecules or oligomers. And the main differences are deposition. Polymers are usually from solution printing, whereas the small molecules are either vacuum evaporated or solution. I will today talk mostly about vacuum evaporation. In organic LEDs, today the commercially applied organic semiconductors are all done with small molecules and evaporation. In the solar cell field, both technologies are investigated, and at least in the lab, they are almost on par. In production, maybe evaporation is a little bit ahead. But that's not really important, but keep it in mind, there are different varieties to deposit. Now, I'm now going again on the NREL chart, but I'm going down here in the noise. The higher regions have been discussed already, and I'm now going here down. I'll show it in large later that you see better where we are. If you look at an organic solar cell, you have to watch it a little bit differently than a CATL or silicon solar cell, because you generate first excitons, they diffuse to an active layer, and there they have to be separated, and then you transport charges and extract them. And the main difference is then that you need an internal interface where you separate these excitons. The reason why you need that is very simple. In the classical semiconductors, you have a so-called one-year exciton, which is very large, about 20 nanometers, and weakly bound, weakly compared to KT. Whereas in organic materials, you have a very small and tightly bound exciton, much, much more tightly bound than KT, so you can separate electron and hole by an electric field, and the usual cell structure doesn't work. The way to solve that was invented by Ching Teng almost 30 years ago. You introduce a so-called heterojunction, a donor-acceptor heterojunction, where you separate the excitons by this energy step. Now comes the second problem. You have not only these tightly bound excitons, they also have to move to this interface, and unfortunately they don't like to move. The diffusion length of these excitons is very small. This is an example of a measurement done in my lab. and we measured that you can transport these only about 10 nanometers. In other words, only a few of the excitons which are absorbed in the material can reach this heterojunction. And the way to solve it is that you move the heterojunction to the exciton by creating the so-called bulk heterojunction, where you mix donor and acceptor intimately in such a nanomorphology. This surprisingly works rather well, but it generates a lot of complicated chemistry and physics, and that's one of the key parts of my talk to discuss that. Also, it is clear from the way we have done this here is that you have an energy loss because the separation of the exciton will lose some energy, and that will reflect in a lower voltage. I will discuss it as well. The separation process is actually a fairly complicated process. I have no time at all to discuss it in much detail, but the basic points is that you first generate the exciton, and then you separate into a so-called charge transfer state, and these charge transfer state then can be separated in carriers, or you can generate triplets. There's a lot of literature around, and I would suggest to read that if you want to know more about it. The key question is how much do you lose going from here to here, and that will depend or determine the voltage and thus the energy losses. The other point is now the control of this bulk heterojunction. As said, the flat heterojunction doesn't really work because the diffusion length is usually not large enough. And ideally, you would have such a structure where you have very nice columns which separate the two carriers. The reality, however, is very different, and the typical length scale of this morphology is on the order of 10 to 20 nanometers, and it's hard to control. I just give one slide from the polymer field where liquid processing is done, and in that field, actually, people have characterized these heterojunctions a little bit better than for small molecules, and have seen many, many very interesting things. For instance, that there is a mixed region which has slightly different energetics, and that mixed regions play a role in the separation. I cannot cover that in detail, but fortunately, there's another session on Thursday, and for instance, my KAUST colleague Pierre Bourjuge will talk about these issues, and some other speakers as well. Now let me switch, and after the basics, address the question how we can improve these efficiencies of these organic solar cells. Ideally, when we do research, we would actually start with the device, and from the device we would go backwards and tell the synthetic chemist, please prepare me this molecule, and that's the best molecule. The reality is unfortunately exactly the other way. We make molecules and we test them in the cell, then we see whether they are good or not, and then we go back to the molecule. We did this process very carefully in a study we did over several years together with Peter Beuerle's group in Ulm. And we looked at what we call the thiophene zoo, where we had a thiophene backbone molecule with two handles. We could change the length of the thiophene backbone here, and we could change these side groups of the molecule. And this way we can change the energetics, and this way we can change the morphology, and we investigated a very large number of molecules. Here you see the energy changes. You can systematically change the valence states or HOMO in organics, and the LUMO is nearly unchanged when you change the length of the molecule. And this way you can also adjust this energy step where you separate the excitons, and you can find out which kind of voltage you can get from these systems. And when we performed these studies, we saw that depending on the number of thiophene rings, we get different voltages. The highest voltage when we have here the shortest molecules, but then as you can see, the fill factor is getting really bad. And here you have a lower voltage, but a better fill factor. And already this study is a number of years ago, we did that. We could find out that you lose additionally about 0.3 volts in these systems to separate the exciton. And that is a voltage loss which reduces the efficiency. To discuss that in a little more detail, I'm taking here some data from a recent paper, which is also partly from my colleague Aram Amassian at KAUST. And what they plotted is the open circuit voltage of organic solar cells, whether the energy of this charge transfer state And basically, you see they correlate very nicely with a shift which is about 0.6 volts, and compared to the absorption gap, which is again a little larger than that, the best organic solar cells lose about 0.6 to 0.7 volts compared to the absorption gap. If you compare that to the best PV technology, gallium arsenide, it's about twice as much. And the key question will be, how much can we reduce this? And at the moment, it's not really possible to predict. But even on this curve, some people have seen some outliers in the right direction, and I'm pretty optimistic that we can reduce at least this voltage loss. Now let me come back once more to the morphology for these small molecule systems. Here again, you see this energy shift with the length of the molecule, but you also see how these side groups change the energy in solution. The light blue, there's not much difference, but if you go to the thin films, you have significant shifts of half an electron volt or more to the different morphology. And when we carefully investigated that, we found that these molecules, the 5-ring, seem to be close to optimum, and we investigate now especially, I'll show you results for 3 different molecules which are almost identical, except that these methyl side groups are slightly differently located. And when we compared, for instance, 2 of those, we saw quite different efficiencies. So this molecule here with the groups in the center had almost 7%, this had about 5%, and we thought, okay, no problem, obviously this is the better molecule, and my student Chris Elchner wanted to find out whether this is true. So what he did is he did scattering studies at Stanford, and I can't discuss that in much detail, but the basic message is that if you deposit both materials at room temperature, they are pretty much amorphous, and then there's little order. And if you increase the substrate temperature, they start to order and get a fairly good crystalline. But as you can see, there's a temperature difference. It's not big, it's about 30 degrees. But since we prepared our solar cells at about 90 degrees substrate temperature, in the one case we had optimized, and in the other case not. So the message is that it's very, very time consuming to test these organic materials, because for every molecule you have to optimize the conditions. In silicon or CATL, you do that once in a very basic picture, but in the organics, every molecule is a fresh start, and that is very time consuming and one of the big difficulties of the field. And due to lack of time, I won't really go into the details, but there's a very complicated behavior of morphology, domain size, and roughness as a function of thickness, which we still little understand. Okay, now I'm going to some more recent results, which go towards higher efficiency. First of all, some single junction cells which were produced by Rico Mehrheim recently, published last week. And we could, with EASE certification, we could obtain 8.3% with this molecule. Note that the active layer in this cell is only 40 nanometers thick. We cannot make it much thicker because we would lose fill factor due to transport problems, but it shows you how highly absorbing these materials are. And the external quantum efficiencies, at least in a range of the absorption, are about 70%, but there's still a lot more room to improve. There will be a talk by Rico on Thursday, so if you want to know details, go to this talk. Now, these single junction cells, as I said, we are here at about 8.3%, have a potential of about 15%. That's a calculation from Tony Müller in his PhD work at my group. And he calculated that for the optimum gap, that for realistic values, you should reach about 15% in the lab, which means that in the module, you'll have about 10 to 12, and that is simply not enough. The way to go is obvious. It's go to multi-junction cell. If you use several junctions, like in the first talk, you can get better. The limit for one junction is 31%, and for tandem, you can reach 42 and 49, and additionally, you have lower electrical losses if you have these multi-junction cells. And for instance, for tandem, Tony Müller calculated that something like 20% is doable. Since the Shockley-Queisser limit is 43, this is still an overall efficiency of below 50%. Fortunately, it's quite easy to do tandems with organics, especially with these evaporated ones. We do PIN cells, and the PN contact in the center is actually already the recombination contact you need, and by these window layers we can nicely optimize the optics. And the recombination contact is these highly doped layers which allow a direct tunneling of the electrons into the valence states. Using that, Rico did also tandem and triple cells, which achieved almost 10%. The external quantum efficiencies, however, as you can see, are fairly low. As you see, the multi-junction cells significantly suffer in current. That's the biggest problem, to match the currents and keep them high enough. And there's a lot more optimization work to be done. This structure looks fairly complicated, but in a roll-to-roll process with multi-sources, it is not very difficult to produce. Our spin-off company, Heliatech, has optimized further with some proprietary molecules, and already 2 years ago or so, they published a 12% result. And the question is again, will this continue? But if you look at the module level, the status is also very good. On the active area, they have achieved already 10%. Once more, you nicely see here that you can change the colors and do it also transparently. This is now the magnified part of the NREL plot, and as you can see, the organics, the small area hero results and the certified results have enormously grown in the past years, even much more than CAD-TEL. The question is, how long will that continue, or will we now have a stagnation? I'm pretty much convinced we can continue this speed for some time. It's interesting to mention that there's a new kid on the block, the Perovskites. You might have heard that recently efficiencies well beyond 15% have been achieved. The best certified efficiency is 17%. A few weeks ago, a record cell was reported, but I must say record is a little bit questionable here, because this is the IV curve, which looks perfect, and it says 19%. It's the best out of many cells. But if you look more carefully at the paper, you find out that it depends on whether you measure it in forward and reverse, and obviously they take the forward part. I mean, this is, in my opinion, borderline. You know, are we now having forward modules and reverse modules? And so I think this community has to improve. We also did some works on these perovskites. It was disappointing for us working so hard on organics, how quickly we got these perovskites to efficiency. This is work from Lauren Pollander. She did a fully vacuum evaporated cell using different hole transporters, and investigated some optimum materials. The main message was also that in these fully evaporated cells, the hysteresis was gone, so then you can have reliable efficiencies. Now, very quickly in the remaining time, a little bit about lifetime. This is a university result from Christiane Falkenberg in her PhD thesis. She compared different electron transport materials. The best one was still C60. And when she did a very rough lifetime extrapolation here, she found 37 years. Now, this won't be achieved in a product today, but it shows the potential, at least the stability of the molecules is high enough to achieve very long lifetimes. Heliatech has published some very nice results. This is a damp heat PV standard test where you can have a 10% decay, and these organic flexible modules have about 3%. So they easily pass these damp heat tests. Another point which is important to mention is that organics is about the only PV technology which likes heat and gets better. This is an example again from Heliatech, and you can see that the efficiency maximum is reached at about 55, 60 degrees, which is exactly the temperature you read in the hotter parts of the world in the module, whereas all other technologies suffer from heat. There are some first data published on the efficiency and comparing different technologies, and the differences are huge. In this case, it's compared to CIGS 38%, and compared to silicon, it's 27%. And this is a measurement from Singapore. In Germany, it was a little less, but at least in the hot parts of the world, it will be better. And this photograph shows me in a really hot part. This is on the roof of the KAUST solar center. And you can see it's a nice place, but I tell you, it was really hot and humid on that day. And it wasn't very pleasant to take these photographs. I keep the modules there, but I go down in the building where it's air conditioned. Finally, a few words about cost, and I'm taking the long-term future. This is a recently appeared paper which did a very aggressive cost calculation for a 3 gigawatt roll-to-roll production with these parameters, assuming very high yields. So as said, it's a radical calculation. The main result is that it's mostly materials. 71% is materials cost. Of those, it's actually not the active material, by far not. It's actually mostly the substrate, because the active material is, as I said, very thin and only 1 gram per square meter. And the numbers which come out are spectacular. They calculated that you can reach $7 to $8 per square meter for a module. If you reach 15% or so in a module, which is doable, this converts to about $0.05 per watt peak. And if you do a very academic rough calculation and assume that you can scale the system costs as aggressively, the kilowatt hour in a hot country will cost about 2 cents. This is now really, don't take these numbers for granted. This is a university professor calculation. But at least the order of magnitude is really radical. We talk about here at best in 50 cents in silicon nowadays, and this is still a factor of 10. I think at the end, electricity will be cheap. It will be expensive to store and distribute it. I can't say much about manufacturing, but this is a research tool we operate at Fraunhofer. It shows this roll-to-roll principle. You have a plastic foil, you unwind it, you coat it, all these layers in one run, and then you wind it up, and you will do these things by the kilometer. There will be another talk on organic PV by Christian Uhrig from Heliatech. I'm referring to that for applications. So I'm coming to the conclusions. We have seen a dramatic growth in efficiencies for organic solar cells in the last years. We've reached 12%, and 20% should be doable. We will need tandem or even triple cells for that, but fortunately they can be done fairly easily. I'm very much convinced that the lifetimes are doable. It's a lot of engineering, but the physics of the molecules is there. And there's a very recent development with the new Perovskites, but at the moment it is still open what the long-term impact will be. And finally, I'd like to thank the many people at TU Dresden, Heliatech, Uni Ulm, and for collaboration and discussions, and I thank you for listening.